use right now. And lastly would be the general knowledge, like to understand the working principles of different pilot learning schemes we have. All right, so let's move to the first slide right now on the introductions. So for whatever scheme we have learned so far, for example, overcurrents predictions in chapters 4 or distance predictions we learned in the previous chapters, that all belongs to non-pilot's prediction scheme. So there are some limitation for such kinds of schemes whereby it's unable to clear the fault at the instance whenever it occurs, especially for those fault that occurs at each ends of the transmissions line. Right? This is because this fault is occur at the edge here is actually relying to the second or more maybe third zones of operations for it to clear the fault. So to further understand this, why we have such kinds of problems, let's check out these figures here. So what if I have a long distance of transmissions line and it has been divided into two sections via substation A, B, and C, right? And right now, I'm implementing the distance protection at each terminals here. So for example, RAB is the distance protections that I have been implemented for line sections A and B. So here as for distance protection, it will consist of 3 zones of protection if you still could recall. So this is the first zones of protection for the distance relay as the primary protections between line AB. Then it consists of the second zones of operation. As you can see, the coverage area is more than the line section you want to protect. So it's also inclusive. Let's say here is 20% of the next line section. So it acts as the backup protections. And at the same terminals here, this distance protection also consists of third zone setting. So you can see it even can cover to the next line section as a backup. Same apply for terminals B here. We have distance relay RBC. So this is the first zone, for example. The second and third zone is not being displayed here, all right, due to the constraint of the figures. So right now, what happens if I have fault occurs at the edge of the line in between A and B here, all right? So if I have this fault occurs, you can see, right, for this distance rate that locates as terminals A is unable to cover it as a primary protections. Why? Because it's outside the zones of protections. But for whatever fault that occurs within, let's say here is 80% of the line, yes, it's no issue. So it can be cleared by its first zones of protection. So right now you can see, right, this fault that occur at the edge of the line will only covered by the backup protection of this distance relay. All right. So the reasons why is because it's being set in this way is due to the under-regime setting of the first zone setting. So with such a case, you can see for those fault that occurs at the edge of the line, we will have delay in terms of tripping the fault, seeing as is relying on the second zones of protection. So right now, the fault at the remote end, either at the beginning ends here or at the ends of the line sections to be protected, unable to clear at the instance whenever there's a fault occurs. So there will be some time delay because we are relying the backup protections to deal with this fault. All right. The reason why is because for this distance relay, or let's say it's an overcurrents relay, is actually using the information to trip those faults within these sections of the line. So what we can say for non-pilot protection scheme, we can't have fast faulty line eliminations. All right. So now to further understand this, let's see some examples so that we have clear views why we have such limitations if we are using non-pilot protection scheme. So suppose this is the long line that we want to implement with the protections. So now here we have terminal, let's say this is terminal 1, this is terminal 2. So it ends of the terminals here, we actually has been implemented with the distance relay. So distance relay is with directional feature, so it will look into the line. So for distance protection, it will consist of 3 working zones of operation. So for example, we have zone 1 setting, and zone 2 setting as a backup for zone 1. So it will be with the time delay in this case is 20 cycle time. And zone 3 will even have more delays of time. In this case is 60 cycles of times. Alright, so both relays at each side, like relay 1 and relay 2 here at the another end, it has zone 1 setting, correct? And zone 1 setting is always being set to be under regimes, all right? So that is only covering 80% of the transmissions line. So as you can see via the animations here, the blue shaded regions will be the zone 1 setting for the relay 1 that locates at the left-hand side, whereby yellow shaded regions will be the zone 1 setting for the relay 2, which is located at the right-hand side of this transmissions line. So from these two zone 1 setting from relay 1 and relay 2, you can see we have overlapping regions. All right, so overlappings of both relay 1 and relay 2. So now, if you look into the step characteristic curve at the bottoms here, all right, this is the line, all right, this is the line. So we have both terminals here, so we have distance protection at each end. So relay 1 will look into the line same as the relay 2 look into the line. So now, which means that it will detect the fault that's located at its right-hand side. So you will see, right, for the first zone setting, which is 80% of the line section, so you can see any fault occurs within this first zone setting here, it will trip without any time delay. And then only it will have the second zone setting for this relay 1 here with the delay times of 20 cycles. And then for the bottoms here, we have relay 2 step characteristic curve. So this is the first zone setting without time delay. This is the second zone settings. All right. So take note that both of the relay will pick up the fault at their own side. So what happens if I have fault occurs? Let's say at the centers of the transmissions line, which is occurring at the overlapping regions of both of the relay. So during these moments of time, whenever there's a fault occur, both relay R1, R2 here immediately pick up this fault. Why? Because if you draw a vertical line like this and look into the step characteristic curve for both relay 1 and relay 2, this fault occurs within the first zone setting for both relay 1 and relay 2. Here, all right, is at its first zone setting. So which means that both relay at both ends will trip the circuit at the same time, so it doesn't have any time delay. So with such a case, what we can say, if we have fault occurs within these green color regions, which is 60% of the transmissions line in the center, we will have no issue if I'm using non-pilot protection scheme. Why? Because I'm expecting to have fast protection scheme. So both relay will send the tripping command through the breaker. So here will open up at both sides. Okay, so what if I change the fault location? So I have it either occurs at the beginning or the ends of the transmissions line. So we understand that for both of the relay 1 and relay 2 here, it has its second zones of protections, right? Let's say it's reached up to 120% down the transmissions line. So you will notice that the orange color regions here would be the second zones of operation for relay 1. So you can see after the delay of times of 20 cycles, it will reach at its second zones. Same goes for relay 2 here that located at the right-hand side of the line. It will have its second zones of operations. All right. Again, after delays, 20 cycles, you will go to the second zones of operations of this distance relay that locate at the right-hand side of the line. So for both of the zone 2 predictions for the relays, it actually will pick up the fault for the remaining 20% of the line, but with the time delays of 20 cycle times. So now let's simulate a fault. What if I have fault occurs near relay 1 here? All right, so if you draw up the locations of the fault, you will notice that this fault is actually occurring at the first zone setting of relay 1. So which means that this relay one will directly pick up this fault as soon as it occurs. So it will send tripping command to the breaker. So here will be open up, no issue. But how about for relay 2? So this relay 2 unable to send its fault within its first zone setting, as you can see, out of these regions here is located at its second zones. So which means that relay 2 at the right hand side, yes, it detect this fault, but it will only send tripping command to these breakers here after delays of times of 20 cycles. So now we can't have fast clear of this fault line for this beginning 20% of the transmissions line. All right, so same goes if I have fault occurs at the ends of the line here as well. So now we know that relay 2 directly able to pick up the fault. Why? Because this last 20% of the fault that occurs on the line is actually occurring at the first zone setting of relay 2. But this is at the second zones of operations of relay 1. So which means that yes, the breakers will open, but you need to wait for 20 cycle time. So with such a case, we can say we will have slow line fault isolations at both ends of the relays here. So it can't trip at the same time for if we are using non-pilot pedestrian scheme. All right, so how actually we can solve this problem so that we have faster fault isolations for the transmissions line, especially for those fault that occurs at the edge of the line. So it leads us use this pilot's projection scheme. So here we have the figure showing the drawing of the pilot's projection scheme is actually a communications assist projection scheme. All right, so now the pilot is being used as the communication channel so that we can exchange the informations between two or more relay within the transmissions. Like let's say the relay send the zone 2 failures. All right, so how actually is worked? So it's like this. So now, whenever we have fault occurs, let's say at the beginning of the transmissions line here, yes, we know relay 1 here able to pick up this fault via its first zones of protection. So it will send the tripping command to the circuit breaker. But at the same time, it will activate this pilots, all right, or the communication channel. So via the transmission port, it will actually send the tripping signal to relay 2 here. Before these relay 2 able to sense the faults here, where is second zones of operations. So imagine it's like you are the one here as the positions of relay 1. So whenever you sense the fault occurs at your site, you actually call your friends, which is located at the ends here, ask your friend to trip the breaker first. So this is how does the pulse protection scheme work. So which means that this relay 2 doesn't need to wait until the second zone's operations here, then only it send the command, is already send the tripping commands to the breakers via the informations you obtain from relay 1. So you can see pilots is actually the communication channel that allow the exchange of informations of both of the relays that look at both ends of the transmissions line. So that's how we achieve the instant clearing of 100% of the transmissions line. So there's another name for pilot's protection scheme is also known as tele protections. Just another name. All right. So now let's move on here. So for communication purpose, there are different communication channel you can use. All right. So here we have 4 choice to use. One is known as power line carrier. In this case, transmissions line itself has been used as the communication channel. We can also use the microwave system, use fiber optics link, as well as the telephone line, the communication cables here, you can use to inject the high frequency signal for data exchange. All right, so the general descriptions, or I should say the understanding of each types of communication channel will be discussed in the next sections so that it gives you the better understanding how actually we can implement it as a pilot's protection scheme. So there will be no comprehensive detailed discussion for each communication channel because it's beyond the scope of this subject. All right, so now let's move on to talk about the earliest pilot's protection scheme we can use is the power line carrier. Power line carrier in short is PLC. The other name you can actually call it as audio tune facilities. So right now, as being mentioned just now, so if you refer to the figures, the transmissions line that we want to protect, right? This transmissions line itself has been used as the communication path for the signals exchange. So right now, the signal is actually transmits via on and off mode. The another name for it will be amplitude modifications or modulations at certain frequency value, whereby you can select between this range 10 to 490 kilohertz of bandwidth over the transmissions line. So let's check out these figures again. It's actually showing a single line diagram for the main components that you can find for power line carriers. So as being mentioned, this is the line that I want to implement with pellets protection scheme. All right, so it will consist of both sides having the component including the line trap, that we have the line tuner, as well as the communication system. Here we have the transmission port and the receiving port. So you will find the same component at the another ends of the transmissions line. So you might wonder why we have one circle here, right and left here. These circles is actually showing you how does the signal is being transmitted or travel via this transmissions line to the another ends of the transmissions line. All right, and here is actually the actual views of how does both coupling capacitance as well as the line trap is being looks like. Right, and the one at the right hand side here is actually showing the one implement for 500 kilowatts of transmissions line, and this is how does the line traps looks like. So let's see the details of this power line carrier operation in the next slide. Okay, so as we know right now, the high frequency signal, which is the data you want to exchange between the ends of the line, will actually superimpose to one or more transmissions line conducted for the purpose of communications. All right, let's say we are talking about power line carrier. So there are two ways for us to achieve this, which is by using the coupling capacitor. So how the signal is being injected into transmissions line. One of the ways is known as single phase coupling. All right. So single phase coupling, also known as line to ground or phase to ground coupling. So with this method, right, you will know only one phase of the transmissions line is being used for communications, with ground used at the signal returning path. So now we have a single phase coupling to coupling high frequency signal into this one phase of the transmissions line. So because we are only using one phase, right, which means that lesser component is needed. So for example, the coupling capacitors, the line tuner, as well as the weight tray, only one set will be enough for each side of the transmissions line. So this is what we have as the single phase coupling. The next one we have is known as face-to-face or line-to-line coupling. So from here, you can directly tell us that now the injections of high-frequency signal has been using two phase of the transmissions line. So which means that the ground path is not being used. And there is also another name for face-to-face or line-to-line coupling is known as interface coupling. If let's say this coupling process has been occurs between the adjacent line within the same supporting tower. So what is the advantages of using this line-to-line coupling? So see as the ground of the line is not being used, so any event happens at the ground path here, like let's say short circuit to ground, will not affect the communication signal. So we will not have the signal loss, all right, as we can see for the phase to ground coupling. All right, so that is the two way we can inject high frequency signal to the transmissions line. One is by using two phase of the three phase line. One is using a single phase line together with the ground path. All right, so now let's move on here. So whenever we are using the power line carriers for signal communications, all right, so we need to block the high power signal, which is, let's say, is operate at 60 hertz or 50 hertz power here, you have to stop it from entering into the communication system. This is because communication system cannot take high power from the line. Let's say it's operating at 230 kilowatt, because this is a long distance of transmissions line. So now how actually we can block this power from entering into the communication system? We need to use these components here, known as coupling capacitor, together with this, the line tuner, the one that circles in red. So by using these two components, we can ensure that there will be low impedance path for a high frequency signal, which is the signal that you want it to be, communicate, then it's able to going in because you have low impedance path. But if you give high impedance path for 60 hertz power signal, all right, so to further understand this, as you can see, capacitor. To find capacitor reactance value, we know that is governed by these formulas, right? 1 over 2 pi Fc is actually frequency dependent. So in the event if I have high frequency signal, which is the signal you want to exchange between the ends of the line, so high frequency will give you low reactance value. All right, so whenever I have low reactance for the high frequency signal, so the signal can be entered into the communication system. But what if I have power? All right, the power from the power plant could be either at 50 hertz or 60 hertz. 50 hertz, 60 hertz is considering low frequency. So if I have low frequency, the capacitive reactance value will become high. So that's how it gives high impedance path for the power. So the power unable enter into this communication system here and fry the system. So what is the purpose of both coupling capacitors as well as the line tuners? All right, so now how far does the signal can be transmitted is actually based on the power output of these power line carriers. All right, so now for example, if you have the power line carrier system with the output power of 10 watt, it can give you the distance transmission for the signal up to about 100 miles. So what if I increase the power by 10 times higher? So obviously, the signal transmissions length can be further away. It can be effective over 150 miles. So you can see that directly proportional to each other. The higher the output from this system, the longer the signal can actually transmit to the other side of the transmissions line. All right, so at the same time, this high frequency signal, which is the signal you want to exchange, right? You have to confine within the line that you want to protect. So which means that if I want to exchange the signal, this signal should not go to the next line section. So it will escape from, let's say, this bus bar here, go to the next line system. So it unable to go into this communication system. So how actually I can confine this high frequency signal between this line is by using the line trap that being placed at both ends of the transmissions line. All right, so now you can see this line trap is actually being formed with both the inductors as well as the capacitor. So in parallel connection, this is actually forming a resonance circuit. So for this line trap line is actually built or tuned in the way where it will give low impedance path for the power frequency, which means that the power that you want to transmit, yes, it can go through and enter into the next line sections. But it will give high impedance path for the high frequency signal, which is the signal you want to exchange between the ends of the line to achieve fast 40 line isolations. So this can be clearly seen by looking into these two formulas here. As we know, here I have inductors as well as the capacitors. So to find the inductive reactance value, I know that is calculated by 2 pi FL, all right, omega L. Or to find the capacitive reactance is 1 over omega C. So you can see both of them are frequency dependent. So right now, both of the reactance value has been tuned in a way to avoid this high frequency signal from escaping from the transmissions line. So it confines within the line that we want to protect. Right, so that's how we ensure there is no escape of the high frequency signals. All right, so for this power line carriers, right, is commonly used as the pilot's projection scheme, seeing as it's an extremely versatile of communication channel we can apply, which can be applied together with the protection scheme, including directional comparison scheme as well as phase comparison scheme. So this one, we will learn about this in much more details later. What is this as a pilot protection scheme? But for power line carrier is start to be replaced with another communication channels we have. For example, the microwave systems or the fiber optics link. Why? Because it's signal, right? The signal that you want to exchange is easily affected, right, by different situations like the lightning strike. So whenever we have lightning strike or we have fault occurs within the line, it might cause the signal loss. So which means that they're unable to exchange the informations. Or maybe if you have fault occurs, so after the trippings of the breakers, this might also affect the signal to be transmitted as well. So that is the problem faced by the power line carrier. That's why it's slowly being replaced by using the microwave systems or the fiber optics link. Okay, so now the next communication channel we will use will be the microwave system, whereby right now the signal can be transmitted using lesser power, but with much higher frequency from this range you can select, which is 150 megahertz up to 20 gigahertz. So you can see the signal band, the frequency is actually quite high. So for this bandwidth, the frequency available, of course, you can use in the pilot's projection scheme in the multiples of 4 kilohertz of each channel, and each of them should be operated in parallel manners. So seeing as the microwave system can be also used for the another purpose as well, because the available range we can select is actually quite large. So not only used for pilot's projection scheme, we could have the remaining bandwidth here to be used for different applications. For example, the voice metering, right, the alarming systems and all. So now takes note that each of the applications here should run at different frequency so that we can avoid the interference to each others. Like pilot's protection scheme at certain frequency channel, that if let's say you want to have a data calling, then it should be at another frequency so that it will not affecting each others. All right, so now let's see how does the microwave system work as a pilot's protection scheme communication channel. So basically, if we are using microwave system, right, it will not having the problem as we can found for the power line carrier, seeing as the line is not being used for communication purpose. However, the range, how far the signal can be transmitted, is actually based on the line of sight path between two antenna, all right, which means that it's subject to atmospheric attenuations as well as distortion. So to further understand this, let's check out this image here. So this is basically the antenna disc. One is actually transmitting, another one is actually receiving. So this dot 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 is actually the signal that's being transmitted from transmitter to receivers. So if let's say you put something blocked in between, the signal will be attenuated, which means that we might have signal loss. So for example, if these two antenna this here, right, is with a tall buildings in between, or probably we have a tree in between, the signal will be lost. So how actually we can solve these problems here is with the usage of repeaters. So for example, every 50 to 60 kilometer, we can actually use one repeaters, right? So in such a case, if I have long distance between these two antennas, there's a need of increase the numbers of repeaters to be used. So for such a case, by using the repeaters, actually it will increase the cost of implementations. So that's basically the problems we might have from microwave system. We must ensure the signal transmit in between must be in the line of sight path. All right, so let's see how it works by using the microwave system to achieve fast faulty line eliminations. So now here is the high voltage transmissions network. All right. So for example, I have fault occurs at the beginning of this edge of the line. So obviously, for the relay system at this side of the line, it directly pick up the fault. So it will issue tripping command to the breakers at this side. But at the same time, it will convert these tripping signals here into high frequency signals. So we have a signal converters here. Then only it will transmit over via the antenna this to the another side. So right now, yes, here I received the signal. This is high frequency signal. It will need to convert it down in terms of frequency. Then only this range system will issue as the tripping command to open up the breaker at the another side. So that's how we achieve faster 40 line animations by using the microwave system. All right, so now let's move on here. We have another communication channels also being rapidly introduced into electrical power system is known as fiber optics links. So nowadays, the fiber optics channels can be used. Why? Because it has unlimited channels capacity. So for example, for one single fiber optics link, it can have up to 8,000 channels to be used. And these numbers of channels can be further increased if I'm using multiple fiber optics links. All right. So take note that the numbers of fibers within the same cables here is depending on the modes of operations as well as the application. So how does the tripping signal is being sent? So basically, the tripping signal will be converted into the beams of light. All right. Of course, with higher frequency, and then it will transmit over using the fiber optics link via total internal reflection. So let's check out these figures here. So this is the fiber optics. So the centers here, in this case, is the core of the fiber optics. And then we have the cladding at the second layer, and the most outer layers here, we have the cable shields in black usually. So now core is where the place the signals is being transmitted. As you can see, total internal refractions, right, is usually a mix of glass. So the second layer here, the cladding, right, is actually used to prevent the loss of light in the cables. All right, that is the purpose of the cladding. And the outer shields here is the one used as the protections for the entire cables. Okay, so that's how we transmit the signal using fiber optics link. So if you move to the next slide here, we have a figure showing the typical construction for the fiber optics cables. As being mentioned, the centers here is being made of glass. All right, so the fiber optics link is mixed of glass, and they will be grouped together using the plastic tubes. And then these tubes, right, will be further insulated with the plastic jacket and then further covered with normalized layers, for example, the aluminum alloy, all right, together with the additional strand members. And the most outer layers here, we have the galvanized steel rod. So you can see steels, it gives mechanical protection for the entire fiber optics link so that we can avoid the breakage of the wire. All right, so overall you can see it's mix of non-conducting material. So with such a case, it can't provide the path for the electrical signal. So if we are using the fiber optics links, right, is inherently immune to the interference in the form of electric or magnetic fields. In short, is EMI, electromagnetic interference. This indicates that the signal not easily being lost. All right. So, however, fiber optics link is rarely used for protection purpose. The reasons why is because it's very expensive. But once it's being made available, it will make an excellent choice of communication channel for link systems because the signal will not being lost. All right, so now let's move to the next one we have is known as the pilot's wire. So pilot's wire is actually the telephone cables that's being shielded with copper conductors. So this is one of the most popular communication channel we can use for parts production scheme. However, it is only suitable for short distance of signal transmission, which is up to 10 miles only. And whenever we are using the pilot's wire for as a communication channel, right, the adequate insulations must be given, which is as high as 15 kilowatt. Why? This is because even small induced voltage in the pilot's wire is actually enough to cause the maloperations of the ring system, which means that we have maltripping. All right, and hence we have low security due to this induced voltage at the neighboring line right now. So now let's check out these figures here. We have the cross sections views of the pilot's wire. So at the center, you will notice that it consists of multi-pair conductors which is twisted. And then we have a thick insulations like polyethylene with the shields, all right, aluminum or made of the coppers here to avoid the interference from outside. And then we have the most outer layer here is actually the PVC jacket. So again, for these aluminums at copper shield is actually used like a filter lah, so that we can filter out the magnetic fields from the neighboring power line here, so that we can prevent electromagnetic interference. All right, so now let's see much more details in the next slide here. So as you have seen from the cross-section views of the pilot's wire, if you look into these figures, center always consists of two conductors twisted like this. The reason why it's being twisted is because we want to avoid the crosstalk. And then here you can see it's being wrapped with the copper foil, the one that I mentioned as the filters is either copper foil or aluminum foil, so that we can minimum the inductive interference from the neighboring line or from the external voltage. And then here there's an additional components here known as the ground lead. The ground lead is actually used to protect the potential from the surrounding ground. So right now, the signal attenuation, whenever you see attenuation, which means we might have loss for the signal. If we are using the telephone wire, the loss of the signal is actually depending what types of cables of this parts wire is being constructed, how long will be, as well as what is the frequency is being operating for signal exchange. So if let's say if I have the pilot's wire being configured as the overhead cables, do you still remember what is overhead cable? Is the wire that has been held by two supporting tower. So which means that is actually exposed to the environment. So it's vulnerable to the induced voltage by the power line fault. So which means that if I have lightning strike or if I have fault from a power line, the signal loss might be signal might be lost. Okay, and what if I have pilot's wire here configured as underground cables, which is buried underground? So these types of pilot's wire, it might subjected to the damage due to the digging activity. So these pilot wire might be damaged due to the excavators, so the signal unable to be exchanged. So here will be the 4 different types of communication channel we can use. All right, so you might wonder, when is the time to use these types of cables, for example, fiber optic, and when I should use the telephone's wire for the communication channel as a communication channel. So the selection types of communication channel for pilot's production scheme is actually depending on multiple factors, including the available cost you have, as well as the reliabilities of this communication channel. So you might have limited budget, so you might need to choose the one which is much more cheaper. For example, the telephone wire. Let's say you just want to have short distance of signal transmission. So you can see they're actually interlinked to each other. So how far would be you need to transmit this signal also will affect the choice of communication channel you can use. So for example, if you want to have the signal to be exchanged with further distance away, you might actually use the microwave system. And the next one you have to consider as well as the factors for different communication channel selections will be numbers of terminals we want to protect for the transmissions line. So if let's say more terminal is needed, which means that you need much higher number channels right now from this communication channel. In this case, the very suitable one will be the fiber optics link. Why? Because one simple cables can give you 8,000 of channel if not mistaken, and it can be further increased by adding the fiber optics link. And the next one here will be in terms of frequency. The frequency you need to transmit the tripping signal. So are you want to have the high frequency? If yes, please use microwave system. It's as simple as it is. So this is the considerations parameters that you need to think of if you want to choose the right communication channel to be used. All right. So now let's move on here. So there are two categories of pilot protection scheme we can use in the communication channel, which is by using these channels here, whether the signal is being sent to trip or to block the operations of the line circuit breakers. So now, whenever the signal has been transmitted over the other side using the communication channel to prevent the trippings of the line circuit breakers, so this time we will have blocking modes of pilot's protection scheme. So usually for this mode is preferable if the communication channel is a part of line, which means that you are using the power line carrier. The transmission line itself can be used as the communication channel. Then we will have it to operate as blocking modes of operations. The other one will be known as tripping modes of operation. So which means that right now, the signal transmit over to the another side using the communication channel to initiate tripping instead. So you ask the breaker to trip at the another side. This is what we have as a tripping modes of operation. So generally, tripping modes of operation is preferable if separate communication channel can be used. For example, microwave system, fiber optics, or the telephones via. All right, so for most of the extra high voltage system, it will consist of two operations modes. So either one side act as tripping operations mode, the other side would as blocking operations mode so that it can have better diversity. Okay, so now we'll start to talk about the earliest pilot protection scheme available, which is known as directional comparison scheme with blocking modes of operation. Whenever you see blocking, means that the signal has been sent to the other side to stop breaker from tripping. So right now, whenever we have this directional comparison scheme with blocking modes of operation, so at every given terminus for the transmission line, it will consist of two relay. One is known as tripping relay, another one is known as blocking relay. Both is with directional features, so which means that it will be able to determine whether this is internal fault or external fault. So let's talk about tripping relay first. So from the names, you can try to trip. So for this tripping relay, it will actually try to trip the breakers whenever it senses the fault occurs within the protected line. All right, so basically, you will have this tripping relay look into the line you want to protect. So it will always ask the breakers to trip whenever it senses the fault within its sensing location, unless blocking signal has been received at either ends of the transmission line. All right, so for this tripping relay, we also call it as a fault detectors relay. Usually its coverage area, we have set it to be overreaching, which means that it can reach up to 120% to 150% down the line that I want to protect. All right, so I could have either distance relay as a tripping relay to identify if we have the phase fault occurs within the line, or I can use the one with ground distance relay. So which means that it also able to detect if there is short circuit to ground, or I can use the directional ground overcurrent relay as well as the tripping relay. But the keywords here is for tripping relay has been set to be overreaching, which is more than the line sections that I want to protect. Then I have another relay and is known as blocking relay. All right, blocking relay also known as carrier start relay here, in which right now it being set to sense a fault that occurs outside the line sections that I want to protect, which means that blocking relay is used to detect if I have external fault. So in terms of sensing directions, it will actually look outside the transmissions line, which is different as comparing to the tripping rate. Tripping rate look into the line, blocking rate look outside the line. So now, why is being called as carrier start relay? Because the communication is actually activated by the blocking relay. So whenever external fault is being detected, this blocking relay will start to switch on the transmitters. So it will send the signal to the another side, which is the blocking signal, to stop the relay at the other side from tripping the breaker. So in general, this is how it works. So if let's say at either side of the line, the blocking signal has been being received. So this indicate that we are either have fault-free line, which we have no fault at all, or we have external fault. So the tripping relay will not work, the breakers will not being tripped. But in the event, if tripping relay sense that a fault occurs within its sensing directions and no blocking signal is being received at either side of the line, which means that this tripping relay will start to take action. So the breakers will trip as usually seeing as we really have the faulty line. So that's how it works. So with appropriate logic applied as well as the information transmit to the other side, both ends can determine whether this is the internal fault or external fault occur outside the line that you want to protect. So to further understand this, let's move to the next slide. So with the diagram, I hope that you can understand the ideas behind for this protection scheme. Okay, now I have terminal A, terminal B, and this is the line that I want to be protected. So at each ends of the line, which is terminal A and B here, I will have two relay, okay? One is known as TR. TR is tripping relay. And the other one is BR, is the blocking relay. So for tripping relay, it will look inside the line. This is a line I want to protect, so it will look inside the line. Whereby for blocking relay, it will look outside the line. So for terminals A here, the blocking relay will look into this direction. So this is the sensing fault directions. So the same set of relay you will find also being placed at terminals B here. So the tripping relay at terminals B look inside the line. Blocking relay look outside this terminals B here. So take note that for tripping relay, it has been set to overreach. So for example, so for a tripping relay that locate at terminals A here, look into the line, so it will set to overreach to next line section. So you can see up next to terminals B, I still able to sense if I have fault occurs here. Same goes for tripping relays that located at terminals B here. So it has been set to be overreach. Okay, and then you will notice that, let's say the both of them, I mean tripping and the blocking relay, that actually the distance predictions. So this relay, right, will actually obtain the currents measure as well as voltage measure from the instrumental transmitter to detect if I have fault occurs at this side or not. So in the event if I have fault detect here, then it will send the tripping command to this logic AND gate. Okay, and at the same time, this logic AND gate will receive command from the other side. Okay, so this is basically how it works. AND gate is being used to compare the input from the local tripping relay as well as the blocking signal received from the other end to see if I need to send tripping signal to these breakers or not. Okay, so now let's try to simulate fault situations. Now we have fault occur at the centers of the line. So if we have this situation, tripping relay, right, look into the line, right, set to be overreaching, which means that both of the tripping relay able to send this fault. So under this situation, it will give logic 1 to the AND gate. Same goes for this side as well. Give logic 1 at the AND gate. But for the blocking relay, look outside the line. So it sends no fault occur outside the transmissions line. So which means that now no fault outside, so which means that there is no external fault situation. So the blocking signal will send to another side. In this case, it will give logic 0 to AND gate. So right now, check out the input to the AND gates, right? We have 1 and 0, right? So it will give 0, which means that there's no blocking for the operations right now for the tripping relay. So both sides, the circuit breakers will be tripped. All right. So the tripping relay doesn't stop from operations. So that is how it's work if we have internal fault. So what happens if I have external fault? Let's say outside this terminals B here. Yes, I know that the tripping relay that locate at terminals A here able to send this fault. So it will give logic 1 right now. And then the blocking relay here look outside terminals A. It sends nothing. So it will not send the blocking signal. Okay. But what happens for the tripping relay here? It sends nothing inside the line. So it gives logic 0 to this AND gate. But for the blocking relay, look outside my E. I see that is an external fault here. So as a result, I will send logic 1 to the another side. So whenever I have 1, 1 to this AND gate, so it will give output 1. Output 1 means that this is the blocking signal. So this relay will stop to trip. All right, which means that the tripping relay, yes, I sense there's a fault, but I'm being blocked due to the blocking signal received for the another side. So that's how the external fault is not being tripped from the system. Okay, but at the terminals here, initially the tripping relay unable to send this. That's why here initially there is no tripping being sent to this side of the circuit breaker. So that's how it's work. All right. So now let's see the properties or the requirements of the blocking modes of directional comparison scheme. All right, so you know that for the tripping relay will always want to operate whenever it senses the fault within its sensing direction before the blocking signal is being received. So if let's say if there's any delay of the signal from the blocking relay, which means that I will have false tripping in the event if I have external fault situation. So with such a case for such blocking scheme, the blocking relay must be said to be much more sensitive than the tripping relay. But this is not easily to be achieved, especially if there is big difference between the fault contributions at both ends. Besides, the tripping relay must also bring prevent to be operating, let's say we have heavy load or unbalanced system situations. So with such a case, the time coordinations between the tripping relay and blocking relay is very important so that we can ensure that the blocking signal can be received. Or let's say we have fault-free situations or I have external fault situations before the tripping relay start to operate. All right. And there is also possibilities that we have a maloperations of such scheme. Let's say there is a failures in terms of the communication signal. For example, the brokenness of the communication channels. That's why the signal unable to be exchanged. Or maybe the relay unable to detect if I have external fault. Let's say you have low voltage supply to relay. So we might have maloperations as well. So under these situations, no signal is being sent to stop the tripping in case if I have external fault. So how actually I can solve these problems here, all right? So to avoid the maloperations, we will use the another scheme here, whereby I have unblocking modes of operations for directional comparison scheme. All right, so you'll find that its operation is actually similar as the blocking modes of operation, just that right now we only have one relay at each end of the transmission line. This relay would be the tripping relay. We doesn't have blocking relays right now. Okay, so now we will have a low energy carrier signal is actually the blocking signal is always being sent as a check by using the communication channel. That's why we doesn't need to use the blocking relays right now. And then let's say we have internal faults occurs. Frequency shift key will be used to rewrite this blocking signal from blocking to unblocking. Okay, so now let's see how actually it works. So now this is the line I want to protect. Okay, so if I'm using an unblocking modes of operations for directional comparison scheme, I only have one relay, which is tripping relay at both ends of the line. So it will look into the line that I want to protect. And as usual, it has been set to be overreach. For example, look down 120% of the line section. So this is for relay 1 at terminus A. This is the coverage area for relay 2 at terminus B. Okay, so what happens if I have fault occurs, let's say, outside the terminus A here? So right now, this relay at terminus A unable to detect this fault, okay, because it's looked into this direction. But for relay B, right, is actually able to sense this fault, okay? But because this tripping relay unable to send this fault, right, the blocking signal still continues send over to the another side, which is at terminus B here. So which means that yes, even though the tripping relay able to send this fault at terminus B, but because I received the blocking signal from terminus A, so no tripping will be occur. Right? That's how we have this comparison scheme. It doesn't work under external fault situations. So what happens if I have internal fault, which is really occurs within the line I want to protect? So right now, both tripping relay look into the line. Obviously, it able to send this fault. So whenever it sends a fault within its sensing directions, right? So initially, I have the blocking signal is being always sending via this communication channel, right? So there's a need to change its frequency value from blocking to unblock. So now both of the relay here will release from blocking, right? So it will send tripping signal to the breakers right now. So that's how we clear the fault within the transmission line. Okay, so now let's see what is the advantages of using unblocking modes of operations for this directional comparison scheme. All right, because we only use one relay, right, tripping relay, there's no need of the usage for the blocking relay, which means that we can save in terms of implementation costs. All right, so blocking signal is always being transmitted over using the communication channel. And because of this, unlike the blocking modes of operation, you must have the blocking relay is much more sensitive. Now, the tripping process can be much more faster. So there's no time delay for the tripping relay. All right. So which means that you doesn't need to wait for the signal you obtain from a blocking relay here to see if I want to trip or not. If I sense the fault within my sensing direction, that's why I can achieve faster tripping process. And at the same time, if I have communication channel failure, it can be easily detected as well. Why? Because blocking signal should always send continuously. If let's say there's a loss of signal, I can directly tell that there are some problems happen for these communication channels, right? So that will be the advantages you can find by using the unblocking modes of operations for directional comparison scheme. Okay, so now let's look into one more scheme that I will give you 5 minutes break. So this time I will talk about what is under-reaching direct transfer trip. So this pilot protection scheme is actually very simple. What we are trying to do is we are using the distance relay together with the communication channel to achieve fast 40 line isolations. So unlike the directional comparison scheme, right, now the distance relay has been set to be under reaching. Like terminal A, terminus B, this is the line I want to protect. I'm using the distance protections. So the first zone setting is set to be under reaching, which is 80% of the line to be protected. So that's why it's not as under-reaching direct transfer trip. So how actually we achieve fast 40 line of isolation is same as what we have explained in the earlier class. So whenever we have fault occurs at the edge of the line, we know that at each side of the line, it consists of first zone's projections, correct? It will able to send this fault directly. So obviously, the relay one here at terminus A directly send tripping command to these breakers. But at the same time, it will activate the communication channel. So transmit the signal to the another side using the pilot. Then this relay 2 at terminus B here will directly send tripping command to trip this breaker before it send this fault via its second zones of projections. So that's how we have faster speeds of tripping at both ends of the fault occurs. Right, so with such a case, this is how does the under-reaching direct transfer trip works. So right now, I will give you 5 minutes break. Then we will continue these topics on phase comparison grading sim. So come back at 4:08 p.m. All right, so 5 minutes has passed. Let's proceed our class. So just now we have seen the limitations of non-pilot production scheme whereby the fault occurs at each ends of the line unable to clear without the time delay. That's why we have communication assist protection scheme, which is pilot protection scheme. Okay, and then we have also go through the characteristic of different communication channel we can use, like the power line carriers where the transmission line is still being used as the communication channels. We have microwave system where the signal can be transmitted by using much higher frequency with lower power. And then we could have fiber optics link with large communication channel capacity, as well as telephone wire. All right, but telephone wire only suitable for shorter distance transmission for the signal. All right. Then we also talk about the directional comparison scheme where you can have it look as blocking modes or tripping modes of operations, right? Usually for the fault detectors relay, which is the tripping relay, it has to be set to be overreaching. And then just now we also have understand how does the underreaching direct transfer trick works as well. The difference between is we are using distance relay and the protection coverage area has been set to be underreach instead. That's how its names originate. So right now we'll start to discuss another types of pulse protection scheme you can see is known as phase comparison relaying systems. So for this protection system, it actually makes use of differential protection scheme, whereby right now it is trying to compare the phase angles between the measured primary currents at both ends of the transmission line. So what happens if the measured currents value in terms of phase angle, it gives us the in-phase situations. So right now, this indicates that there's no fault occurs within the protected line unit, whereby if the two measured currents giving me the phase angle, which is up of phase by 180 degree. So this time it will register that is a fault occurs within the line sections that we want to protect. So for phase comparison relay systems here, we can use any communication channels. All right, the four kinds of channels, yes, you can use. All right, so now let's move on here to the next slide. So let's check out these figures here. Is actually the constructions of these schemes. All right. So this is each end of the line that we want to protect because we want to measure the current angles at both ends. So you will notice that we are actually implementing three-phase current transformer to measuring the three-phase current at both ends of the line that we want to protect. So this measured current value will actually fit into these components here known as composite sequence networks. Is actually what we have is the summing transformer. So it will combine the positive, the negative, as well as the zero sequence current here into one single output, which is the single phase output voltage. So here the output will be the voltage. Okay, so this generated voltage, right, is magnitude as well as phase angles is directly proportional to the three-phase current that is being measured at each side. All right. So after this voltage value will be fit into this square wave and amplifier here, whereby whenever you see square wave, which means that we are trying to change the sinusoidal signal into the square wave. So after this, it will fit in here. All right. So depending on the fault detector, so fault detector here is actually the relay we use. So based on the local fault detectors here, yes, it will detect whether we have fault occurs here. Then it will send in the input to the logic and gates here. And at the same time, we have another FD2 here, fault detectors too. So now you can see we have two relay cascades, right? So the second relay here is look like the blocking relay. So whereby it will see if we have external fault or we have fault-free situations, then it will activate the communication channel and send the signal to the another side where we have another AND gate here at terminals B here. All right. So this square wave will be used to key in these channels here and send it over to the another side. So you can find the same components has been used at the other ends of the transmissions line. So, and the logic AND gate here is being used to determine whether I need to trip or not to trip the breaker at my side. Okay. So now let's move on here to the next slide. So let's see how does the system detect if we have fault by referring the measure phase angles value at both ends of the transmissions line. So now you can see we have a figures here showing the measure current, all right, with its respective directions in between line A and B. Okay, so you can see because we want to measure the current and each ends we are using a current transformer to measure the current value. This measure current, of course, will convert into the single phase voltage and then feed into the square wave. Then it will fit into this two level fault detectors. FD here is fault detectors. So this fault detector basically is the relay we are using. So it could be the overcurrent relay. So you can treat the fault detectors. One here is like the tripping relay we have just learned, whereby it's responsible to send the output through the local AND gate. Where FD2 here, the fault detector 2, you can treat works similarly as the blocking relay. So it will actually turn on the communication port and send the signal to the another ends of the line. So this would be the typical components you can see for the phase comparison relaying system. All right, so now let's see how it works. So let's say we simulate different fault situations. So we have F1, F3. F1 and F3 is actually considered as the external fault. So right now, the measured current at both ends, right, the phase angles will be in phase. So which means that the relay sense no fault occurs within the line directions. Whereby for F2 here, which is located at the centers of the line, so obviously this is considered as an internal fault. So the measured currents right now, the phase angle will be out of phase by 180 degree. All right, so here will be the respective measured currents waveform. All right, so the upper sections here is the measured currents waveform at each end, considering we have external fault, which is either F1 or F3. And the lower graph here is those signal we measure in the situations if we have internal fault. Now let's see how does this phase comparison system works here. So in the event if I have external fault, all right, under the situations if I have fault occurs, let's say outside terminus A here. So this is the measured current at terminus A, okay? And this side of terminus B, this is the measured current. So obviously this measured current need to convert it into square wave, all right? So the positive polarity, right, will convert to logic 1, okay? Whereby for negative polarities here will convert to logic 0, all right? So this square wave will be sent into the local AND gate, okay? And at the same time, this converted square wave at terminus A here will send it over to terminus B. So you can see 1, 0, 1, 0 for the first half and the second half. This is the signal obtained from terminus A. And then how about for terminus B here? Let's say this is the measured current in the event if I have external fault. Negative polarities will give me logic 0. Positive polarity will give me logic 1. And this signal will send it over to the local AND gate, not local AND gate, at the AND gate at terminus A here. So you can see the same signal is received at terminal A. So right now we'll fit this at the input to the AND gate. So now let's refer the truth tables here to see whether under external fault situations, if that is tripping signal is being sent. So if you consider for terminus A, all right, so this is the signal I obtained, all right, via the local fault detectors, all right, so I have 1, 0. So first half, 1, second half, 0. And then at the same time, I have the signal received from terminus B, so I have 0, 1. So I have 0, 1. So this is for terminal A side. Okay. At terminal B side, this is the measured current. So I have 0, 1. So I have 0, 1. And then at the same time, I receive the signal from terminal A, so which is 1, 0. So I have 1, 0 here. So for the AND gate, right, let's say whether have a tripping signal being sent or not is based on what will be the input sent to this AND gates right now. So right now I have difference from the input 1, 0 or 0, 1. So every time I have difference in terms of input signal to the AND gate, so which means that it will always give me logic 0. Logic 0 indicate that there's no tripping signal is being sent to the breaker. So now, under accident fault conditions, no tripping signal will be sent to the breakers, right? So how about if I have internal fault? So at terminal A here, this is the measured current, and here is the respective square wave 1, 0. And 1, 0 here will send to terminals B, okay? And then for terminals B here in the event if I have internal fault, all right? So the sensing directions, the current direction will swap, flow into the fault. So this waveform will convert it into square wave. So here, positive half, we have 1. Negative second half, we have 0. And this value will be sent to terminal A as well. Now, let's fit this input value to the truth tables right now. So considering A side, we have 1, 0, 1, 0. So 1, 0, 1, 0. Then terminals B here, this is the local square wave. So we have 1, 0, 1, 0. And the receive signal from terminal A also 1, 0 as well. So from here, as long as both signal is equal to 1, the output from the AND gate will be 1. 1 indicate that this is the tripping signal. So from here, you can see every positive half signal, there will be tripping signals being sent to the breaker. So that's how it's trip the internal fault. Okay, so now let's move on here to see some important notes if we are applying the phase comparisons link system. So for this protection scheme, right, it's only applied to protect the line against the fault that occurs within itself, which means that the internal fault. Why? Because it works based on differential protection scheme. It should work as unit protections. So this means that it doesn't provide backup protections for those faults that occurs at the adjacent line, or even itself doesn't have backup protections. Right, so in the event if I want to have backup protections if I'm using the phase comparison ring system, so this means that I will need to add additional relay at each terminals here so that I'm able to get the backup protections, so I'm able to do the maintenance works, let's say on the communication channels. So even though there is no backup protections, if we are using this scheme, it's actually considered as an advantageous. Why? Because both primary, which is phase comparison ring system, as well as backup relay that you top up to this system here, is actually forced to be worked independently. There are no need to be coordinations with each others. All right, so moving on here, if we compare with directional comparison schemes or even with the direct transfer trip, all right, so these two schemes is actually worked by combining both primary and backup protection. So this is easily to be understand. So as you can see, for direct under-reaching direct transfer trip, right, we have backup and primary protections worked within the same terminal. But for phase comparison scheme, we doesn't have this. Okay, so if you go to the next slide here, seeing as we need to measure the phase current at each end, all right, and its operation is just based on the line current value. So which means that this phase comparison ring system here, its performance doesn't being affected by those issues you can find for the distance protections. For example, the power swing situation from the generation plant, or out of step situation, out of synchronism for the generator, it will not affect it. All right. So because it's only work based on the current value, it doesn't need to get the voltage or like divide voltage current to get the impedance value. No. So with such a case, no potential transfer is needed. So which means that we can save money in terms of implementations, especially for extra high voltage systems. Right, so there's also an advantages if we are applying this phase comparison string system whereby seeing as it doesn't need voltage value to establish where is the fault directions. All right, so basically you can see whatever you can find, right, the problems at the distance protection, it can be solved by using phase comparison ring system. Okay, so what else we have here? So the next protection scheme could also use as product protections is known as current differential protection scheme. All right, so right now, this is the well-known principle whereby we are trying to compare the current value, the current which is entering and leaving from the lines right now. So under normal situations with no fault at all, the difference between the entering currents and leaving currents should be equivalent to zero, all right? Or it can be equal to any tap load on the line if, let's say, the feeding current at both ends is not same, all right? So the value will be changed based on the locations of the fault. So in practice, the setting for the relay, I mean, now we have the differentials relay, right? It should not equivalent to zero, I mean, for the pickup currents value. This is because this is not practical as we might have the mismatch coming from the current transfer side. It has different current transfer ratio, right? Let's say we have accident fault situation, we might have the spills current flowing through the relay operating coil here. So we might have mild operation if, let's say, you set it at equivalent to zero value. Okay, so the informations relate to the phase angles as well as the magnitudes of the currents runner at each terminus of the lines right now must be mixed available so that we can prevent the maloperations in the event if that is accident fault. So with such a case, if we are using current differential protection scheme, communication channel must be provided so that it will not maloperate. Okay, so now let's move on here. These communication channels could be the metals pellets wire, the audio tunes over leads pellets wire, microwave, or even using the fiber optics link. However, power line carrier is not suitable for the implementations of this current differential protection scheme. Why? Because large bandwidth is needed. So if you still could recall, the power line carrier, the frequency available for us to use is just between the range from 10 to 490 kilohertz. So with such a case, it becomes not suitable. All right. So there are two main types of current link systems we have. So how does the signal is being communicated? So let's see. So one way is by having the measure current at each terminus here being fit into the composite network. All right, and then it will compare over through the communication channel. So this is the first way how the signal is being communicated. The other way is each measure current you will need to sample it and convert it into digital data. Then only you transmit over to the another side. All right, this is the another way. First is in AC value. Another one is in terms of digitals value. This is analog. This is in terms of digitals. All right, so it's very important to take note that for current differential schemes, it actually tend to be more sensitive to the distance protection scheme. Why? Because it's only respond based on measure currents value. No voltage device is needed for its applications. All right, so now moving on here, let's see what is the advantages of using differential protection scheme as pilot protections. So of course, no voltage is needed for its operation. So basically, the problem as what I've been saying just now, the effect by distance protections like power swing situations, the blow fields will not cause it to be maloperating, but it is much more expensive in terms of applications. So beside the transmissions line, current differential has become much more popular recently due to its inherently able to accommodate multi-terminal line with proper logics applied within the relay. So which means that it's able to monitor all current input within the same system. And at the same time, it's also able to differentiate. Right now, we have the transformer, it's just being energized, or maybe we have the inrush currents. Why? Because it's able to detect the difference between the second order harmonics, even the fifth order harmonics. So with such a case, it allows us to apply the line with current differential protection scheme. Let's say it consists the tap transformer. So right now, with appropriate voltage being applied to relay, it can also serve as the backup for distance protections as well. All right, so now let's move to the next scheme we have. Is known as pilot wire relaying system. So as we know, the pilot wire relaying systems here is operation is actually a form of differential line protections. So it's actually similar as a phase comparison scheme we have already discussed right now. It's just that the phase angles of the measured current is actually compared over the pair of the metallic wire, which is via the pilot wire. So there are two variations of pilot wire relaying system. One is known as tripping pilot, another one is known as blocking pilot. So let's see what are the difference between them. So here the figure is showing the basic arrangements of the tripping pilot wire system. So you can see at each terminus for the line that we want to protect. So it will consist of the current transformer at each end to measure the current value. So this measured current value will fit into the mixing networks, and hence single phase output voltage will be generated. All right, so seeing as the measured current, the three-phase current has converted into the single-phase output voltage, so it have this problem whereby the fourth phase identification is actually lost. So right now, the relay will be fit with the restraining coil. So restraining coil is the one that try to hold the operations, all right? So which means that it will not operate. Let's say we have normal situations. At the same time, there is operating coil. Of course, whenever we have current flowing through the operating coil, it tries to trip the circuit breakers. So right now, this operating coil here has to be set much more sensitive than the restraining coil. And after this, here you can see we have the transformer. So the voltage jet from the mixing networks here will fit into this insulation transformer. So it will produce the circulating current flow through the pilot wire to the another end. Okay, now let's see how it works. So now let's say we have internal fault, which means that we have F2s right now occurs within the line that we want to protect. So the measured currents at terminals A as well as terminals B will be out of phase by 180 degrees. Alright, so with the fact that the phase angles of the voltage will actually depends on the measured current, so the voltage at both ends will also out of phase by 180 degrees as well. Alright, so this can be clearly see if you look into this waveform here. So this is terminal A, this is terminal B. The measured current fit into the mixing network, so it will generate the voltage value. This is at A side, this will be at B side. So you can see they are actually out of phase by 180 degrees. And because of this, right, it will actually cause the circulating current flowing through the pilot wire like this, following the red colors arrow. So it will flowing through the operating coil, all right, at both ends of the transmissions line. So now this operating coil is more sensitive than the restraining coil, so which means that here will generate the operating torque. So this indicates that there will be a close connection for the tripping circuit. So tripping signal will be sent to the circuit breaker. So that's how the internal fault is being tripped. Okay, but what if I have external fault occur outside? Let's say at terminals A here, either here or here is considered as a terminal fault. So under these situations, the measured current at both ends here basically will be in phase. Okay, in turn, it will also cause the output from the mixing networks here to be in phase as well. So because both of the voltage is being in phase and supplied into these insulation transformers here, it will cause the current flow like this, all right, following the blue color arrow. So it will go through the restraining coil right now. So which means that this relay will actually restrain from operating. So under these situations, if we have external fault, no trippings will be occurred. So that's how it works. Now the current has been sent to the other side here. Let's say for tripping pilots here is asked to trip. If let's say it flow through the restraining coil, so it will stop operating. Okay, because now we have external fault situations. All right, so now there are some problems, all right, that we have to face on if we are using tripping pilot ring system, because this scheme need the second current to trip the circuit if, let's say, we have internal fault. But in the event if the communication channel has some problem, for example, open circuit, under this situation, no trippings will be occurred. On the other hand, if let's say the pilot's wire here is short circuit, so if let's say it's short circuit, so which means that we have mild tripping. So even though no fault, that is mild tripping. So any problems occurs on the communication channel like open circuit or short circuit will actually cause it to operate strongly. So how actually we can monitor if we have problem for the communication channel? So to see if there is an open circuit or short circuit condition for the pilot's wire, we will actually apply this a few milliamp of DC monitoring current through this pilot's wire. So as a result, whenever there is a change for these DC signals here, this indicate that we might have open circuit or short circuit conditions for the pilot's wire, and hence it will trigger alarm to alert the operators. Okay, so now this is for tripping pilot's modes of operations. So how about for blocking pilot's wire relaying systems here? So the components we use is actually the same. What is the main difference between the tripping modes as well as blocking modes of pilot relaying system is like this, which is the locations of both restraining circuit, or I should say restraining coil, and the operating coil is actually interchanged. And the next one here will be the phase relationship between the voltage output for both internal and external fault is actually reverse as comparing to the tripping pilot range system. Okay, so this blocking pilots right is actually make use the concept of blocking modes of operations, whereby the secondary current in the pilots right is used to prevent trippings of the circuit breaker. So which means it's trying to stop the breakers from tripping in the event if there is accident fault. So right now, any issue occurs on the pilot's wire like open or short circuit conditions. All right, so for example, if we have a open circuit conditions here for the pilot's wire, is actually reverse as comparing to the tripping pilot's modes, whereby we will have forced tripping. So if let's say we have short circuit here, this means that no trippings will be occurred. All right, so the remedy, which is the solution to solve the pilot's wire communications problems here, is also the same, which is by using the DC currents monitoring system on a pilot's wire. Okay, so now let's watch one videos here. So I hope that this video can give you a better understanding how does this protection scheme work. So let me change my screen.
In the old pilot wire systems, we use a three-phase to single-phase summation transformer, as shown here. What this device does is convert the three-phase currents into a single-phase voltage signal, which represents the magnitude and phase angle of the three-phase currents. This means that we can transmit the signal over many kilometers. When the feeder is energized, so the single-phase voltage phasor generated by the summation transformer will be the same at both ends if the three-phase currents are the same. The way that this information is used will depend on the design and manufacturer of the differential feeder protection relay. Some relays will measure the current that flows down the pilots when there's a difference between the single-phase voltage vectors.